let's talk about this chapter here, chapter 4, where we talk about the training models, because this is interesting stuff that's not covered in much detail in the projects. So we're going to talk about things like gradient descent and polynomial regression and some of the other related more advanced features. So linear regression, this is just fitting a straight line to data. So like I say, something I started doing 50 years ago. So the old-fashioned way is to use closed-form equations to compute parameters, which is possible sometimes. If you don't have something you can solve analytically, then you use gradient descent. You have a cost function that measures whether your fit is good or not, and then you tweak the parameters to move to a better fit and a better fit gradually, getting there. And so you can use batch, mini-batch, or stochastic gradient descent. And so here's linear regression, and it's one we talked about before, where you might say, I'm going to assume that I can take a linear function of the GDP and predict how happy people are, life satisfaction. So I want to find the best fit to country data for this. And so that's the equation here. And if you had multiple input parameters, it would be an offset plus a different weight for each of those parameters. Here we only have one parameter, GDP. So the cost function, this typical one you use, is the mean squared error. You take the predicted value, which is the sum of the parameters times x, and then you subtract the real value and you square that. That's this is a really, mean squared error is the most common error, and so all right, so that now you can in principle calculate the analytically from that cost function with a matrix inverse and such here. And so with that, you can just form a function and you can find the best line that goes through these points. That's been around forever. You don't even need a computer for that very much. And this is what I did, like I said, in Fortran many years ago, was pit these sort of things with simple computer programs in Fortran. But it's the simplest kind of machine learning if you want to look at it that way. And so for computational complexity, the matrix inverse takes approximately n squared calculations. And so the overall computational complexity is n to the 2.4 to n cubed. So that's relatively fast. And yes, I see your chats, DM. Good. All right. And so if you can't use the closed form equation because there's a lot of features or too many training instances, then you use gradient descent, which is what we're using in essentially all the projects here. That's the general solution. It's not likely that your model is so simple that you can just use straight up analytical methods. So gradient descent works like this. You have a cost function and parameters, and you just take a step to make the cost go down and down and down, and you just take a whole bunch of steps until you find a minimum. That's the idea. And of course, what you're hoping is that your cost function has a nice simple bowl shaped like this, so you can find the minimum, and it doesn't have some nasty shape with like a local minimum and a better minimum over here, because you might get stuck in a local minimum that's not really the best in such a case. Now, if your learning rate is too small, you'll do many, many, many steps and still not get to the bottom. If your learning rate is too large, you'll take a step, but it'll be too big and take you up the other side and up this side and up this side, and then you don't really get to the bottom. You just sort of bounce around. So you have to find the best learning rate. And here's, like I say, another problem is you might get a local minimum. You might stop here and never find this, or you might hit a plateau where there's no real slope, and then you'll just sort of stop here without getting down there. So both of those are a risk. All right, so the mean squared error, one reason why this is great is none of that will ever happen. It's a convex function. It'll just keep getting bigger and bigger as you move off the minimum. It's a continuous function, so it always has a nice slope and it only has one minimum. So if you can use the mean squared error, it's better. However, it does have the defect here that if and remember I mentioned before, you want to normalize the features so they all go into an expected range like from 0 to 1. If you let some feature go like from 0 to 1 and another feature goes from like 0 to 255, then you'll have a stretched bowl like this, and then if you start out here, you might have a really slow convergence problem finding your way in. And this is a problem that hits a whole lot of machine learning models, that they really don't survive a rescaling of one axis. That's why you typically have to pre-process the data to scale all the features to have a reasonable dynamic range. And so here, now another thing is, you might not want to waste time calculating the cost of every data point on every iteration. It might be easier to just use a batch, a subset of the data for each step, because it'll be faster to calculate and it'll be good enough to move you in the right direction. So you calculate the slope of the descent. If you use the whole training data, it's slow on large training sets, but you can use batches. So this, you have various learning rates. We're trying to fit that line, and the learning rate is too low. So I think we started here, but we went hop, 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 and even after many cycles, we haven't made it up there. Here's a good learning rate. You take big steps up here where the slope is high, and then you slow down when you get here, and you get zoomed in. If the learning rate is too high, you start down here, you jump up here, and you bounce around, and you just end up getting further from the truth instead of closer to it. So one thing you can do is a grid search, where you just try various values of learning rate and choose whichever one seems to converge best. And then there's stochastic gradient descent. Gradient descent uses the whole training set for each step. Stochastic gradient descent picks a random instance at every step and computes the gradient from just that instant. This is, of course, much faster. It only uses one data point for each set. And surprisingly, it works pretty well. In principle, the cost does not decrease with each step because you got this direction from just one parameter, but it does decrease on the average, and it can get you there. And this can have the property of jumping out of a local minimum because you're basing the next step on just one data point, so you can take you can take a surprising step that doesn't follow the real slope down. Sort of like adding noise to each step. And then you can have a learning schedule where you change the step size according to a pattern to optimize it. And this is related to simulated annealing, which is another machine learning method where you have data points like marbles, and you start at a high temperature where they're all jiggling around, and then you cool the temperature where they take smaller and smaller steps to try to condense down to the optimal solution. So you shuffle the data to make it random. If your data is not random, of course, then you'll have a bunch of instances that are all in one category, and then it switches to another category, and then all the steps you take based on this are biased, and then you're biased another way, and that's bad. So you'd want to shuffle your data or pick your instances randomly. And then there's mini batch. Instead of you going to the extreme of using just one instance or the other extreme and using the whole data set, you choose a batch. And a lot of people say the optimum batch is 32. Choose a random 32 instances for each step. That's what a lot of people like to recommend. And so here's batch learning, where you use the whole data set for each step. And you can see it's taking an awful lot of steps here, tiny little steps to get to the optimum value of the parameters. Here's stochastic, where you choose just one instance, so there's a lot of noise and it never really settles down. And then there's mini batch, where you choose like a group of 32, which could be seen as perhaps the optimum, although it also never really settles down. Another issue is, what if you want to fit a nonlinear model? Your data is not going to fit with a straight line. You want to use a high-powered model. So here's quadratic data, like the kind I used in an earlier project. You're not going to ever put a good straight line through this. You have to use a quadratic function to fit in there. And so what you do, this is the brilliant trick. You remember we said you can add new features by calculating them. So you have feature x1. You just add a new feature, which is the square of x1. And now it'll be a straight line on that feature. And the fact that one feature is not independent of another feature doesn't really matter. That's almost always the case in machine learning. You have multiple features that are not really independent, but that's okay. And now you have two values, for instance. You have x and x squared. And you can fit it with simple linear regression. So that's fun. And let's do a Kahoot, which are here, and 4a is here. Oh my goodness. She may be gone. Okay. All right. It's kind of funny. Music is a little scratchy. Unless that's an artistic activity, it's just a networking problem. Anyway. Blow a fan on my computer in case it's my computer getting too hot, which happens sometimes. All right. Whoa. All right, I'll wait a few more seconds in case more people are coming. Okay. All right, good. A couple people left early. That's all right. Okay, farewell.
I have to laugh, Sam. This is not early.
Okay. All right, so which method finds the best fit with a single calculation without iteration? Yeah, that's analytical. Use a closed form equation. You can just go right to the optimal solution for a simple case like mean squared error in a straight line. Which one uses only one instance for each step? Which sounds insane, but people do it. Yep, that's stochastic gradient descent, and we've in fact been using it. I think it is the default for quite a few of these models. And which one adds powers of features as new features? Well, the Kahoot seems to work, except there's a defect in the music somehow, but that's polynomial regression. All right. All right, that's Ryan, who's won 3 times. Very good. And Tina has won 3 times. Good. And Diana has won twice. Good. All right. Now let's go back to here. Okay, so the learning curves. The line underfits this data. If you have 300 parameters, then you can create some insane wobbly things, which is of course not going to generalize. This is overfitting. It might fit these points, but obviously it's not going to fit new points. 2 degrees of freedom is the one that catches the trend, but not the noise. Second degree polynomial. So another way to measure your performance is training error and validation error as a function of iterations. And so you can see as you go through more cycles of training, does it converge? And here's the training.
I'm still seeing Kahoot.
Still seeing Kahoots.
Not your screen.
Are you looking at Twitch?
I'm trying. Maybe it's Maybe I somehow closed it. I'll go back.
Yeah. Just maybe you have to refresh the Twitch. Sometimes you have to do that. Good. Let me know if anything bad like that happens. I can see the Twitch is working here. When you refresh the Twitch, do you see this slide underfitting linear model?
Yeah, I got it now. It's still refreshing. Thank you.
Okay, good. Now let me know, because this is every system has some bugs, and I want to make sure you can follow along. All right. So anyway, here you see you start with the training data having a very low error, which is a little hard to understand. But anyway, this is the solution. It's very far off. And then as you train, it gets better. That's why I'm a little confused about this. The error shouldn't have been small and get bigger. But anyway, then you have this. And the validation and training data will hopefully both converge to the same thing. Now you've got a good fit where the equivalent, where you're getting the same accuracy on the training and the validation data. All right. Oh, I see. This is underfitting. Oh, I see. So it can fit training. We're not doing it by iteration, we're doing it by size. So if you give it only 1 or 2 points, it can fit it perfectly. As you give it more points, it's less than perfect at fitting it, and then the model plateaus, and the error converges to a high value, because this is when you're doing something like putting a line through quadratic data. So the fit is terrible, but stable. There is a line that fits it best, but it doesn't fit it very well. Now I understand. Okay. Now here is when you're putting a 10th degree model on. And now, on the training data, you can fit up to 10 points perfectly with all those 10 parameters. And as you increase, it will, of course, have more and more error. And the validation data will come down, but the two don't match because you are overfitting the training data. So you're getting more accuracy here than you're going to get on the validation data. You're putting in wriggles that are not reflected by the actual underlying population. So bias is underfitting with wrong assumptions, like using a model too simple. Variance is a model with too many parameters, so you overfit. And irreducible error is the actual noise in the data. You can never get the error below that point, of course. And if you increase a model's complexity, you will increase variance and reduce bias. You'll start overfitting more. So you want to regularize your model. You can do it by using lower degree polynomials, or you can constrain the weights. And there's 3 popular ways to do it for a linear model. Ridge regression is the simplest. You have the mean squared error, and you just add a sum of all the slopes. So it prefers less slope. So it penalizes you for having steep slopes in any of the parameters. That's one way. And you just have a parameter here. Alpha is the hyperparameter that controls how much of that you put in. So you can regularize it by just causing it to use shallower slopes. All right, and so here's various levels of ridge regularization. We're fitting here with alpha of 0. You fit the best line through here, and if you increase alpha, it favors flatter models. And here's how it would be for a polynomial model. You have a if you just fit the data with no constraint, it'll fit this high degree polynomial that's waving, but with ridge regression, it will get a smoother one where the coefficients of each polynomial term are forced to be smaller. So you accept a less perfect fit of the training data to get something which will generalize better to the test data. And here's lasso regression, where instead of using the sum of the square of the parameters, you use the sum of the absolute value of the parameters. And the reason you do this is because you have some weights that are far from the mean, and you don't want to overcount them by squaring them. It amounts to the same thing. This is called the L1 norm, where you take the parameters to the first power and the absolute value of them, and this one is called the L2 norm, where you square the values. All right. And so lasso regression, you see it's working here where alpha is 0, you get the line, the dashed line, and as you make alpha bigger, it goes to a flat line. And the same thing here, alpha of 0 gives you the wavy thing, and higher values of alpha give you a more smoothed, regularized fit through it, and values of alpha that are too big force it to have 0 slope, and that's of course no longer very useful at all. And then there's something called the elastic net, which is just a mixture of the two. You have the squared parameters and the absolute value of the parameters, and you have a parameter say how much is to be mixed. So it's a mixture between the previous two. All right. So linear regression without regularization is usually not good. Ridge regression is fine, typically. Elastic net is preferred. Various recommendations. All right. And like I mentioned, early stopping is a very nice way. If you're doing gradient descent, you just go until it first starts to get worse, and then you stop, because clearly you're at the bottom. This is an easy form of regularization. And then there's logistic rejection. This is the way to use a regression algorithm for classification, which is a different job. So I want to say whether an email is spam. So what I do is fit some kind of parameter, and then I just choose a threshold. If the output is bigger than a certain amount, I'll call it spam. Otherwise, I'll call it not spam. So you have a logistic function, which is the output of the prediction, and then whether this is the probability function to tell you the probability of it being spam. The higher this number, the more likely it's spam approaching 1. And the lower this number, the more likely it's not spam approaching 0. So you have a cost function, and this is a way to measure whether you're right or wrong in a classification task. So you take the log of the probability minus 1. This is the cost function. So if the prediction is 1, and the right answer is 1, then this will be near log of 0, which is near minus infinity. Let's see. It gives a low probability for a positive instance. That's an error. And then you'll get a large cost. P will be near 0 in the top row. Yep. Because you'll be predicting a low probability. If you have a high probability for a negative instance, then P is near 1 and you get a large cost. So this is one way to get a function which will measure the cost of a classification, a binary classification of true or false. And so, all right, it's not like the mean squared error. There's no closed form solution, but the cost function is convex, so you won't have the problem of local minima, and you can use gradient descent. And so this is a common data set. They measured the petal, the sepal, and some other parameter of these flowers, and they're trying to sort them into 3 species of irises, versicolors, setosa, and sepal. And so you have 3 features measured in centimeters, this thing. And when you're trying, and you can try to predict from these numbers which one of the breeds it is. And so here, if you use just petal width, this Virginica has wider petals, but there's some overlap. So here's the example of ones that are Virginica. Here's the range of petal width. And here's the other 2 categories, both of which are generally lower, but there is some overlap. So using petal length and petal width, now 2-dimensional, here's what you have. Iris Virginica are the green ones, and the other breeds are down here. So as you can see, there's a pretty good separation, and just having a line somewhere around here would probably be the best decision boundary. So, and we'll do models like that in the hands-on stuff later. All right, so I'll do one more Kahoot, and that'll be all the demonstrations and lectures for today. I bet if I logged out and logged in and reloaded these Kahoot pages, the music would get fixed, but I won't bother right now. I was teaching some of these to a class of Saudi Arabian students, and they told me that music is forbidden. You have to get rid of the music on the Kahoots. So, reminds me of the fundamentalists I grew up with in Pennsylvania, where dancing was forbidden and playing cards was forbidden and stuff like that. So, anyway. But I guess they have no music, like not even in church.
77. 76, 73.
All right, I'll wait a few more seconds, see if anybody else is coming. Looks like the music finally died completely. No, I guess not. All right. All right. All right. So what is caused by overfitting? All right, they call it variance. Although I would like to think generalization error is a pretty good answer too. Let me go back to that slide, see if I want to modify that answer, because okay. Yeah, variance is caused by overfitting. Okay, but generalization error would seem to me like a fair term for it too. But I guess that's not the official term. All right. Anyway, that's kind of nasty one. Anyway. All right. Which method uses L1 and L2 norms? All right, that's elastic net, where you can go between these two and combine them. All right, and which method uses the absolute value of the errors? All right, that is lasso. All right. Mike. All right. And Diana has won 3 times. And Ryan has won 4 times. All right, good. All right.